So we're going to look at, in this next section, curvilinear motion. And back in the last chapter, I think it was maybe the 4th section, we looked at the derivative as a rate of change. You know, just that's one thing that kind of defines what the derivative is. The derivative tells you how one function is changing. And we were able to kind of solve some problems or answer some questions that, you know, if I have a function that describes displacement, then if I take that derivative, I get velocity. That's a rate of change, you know, with respect to time. When we did that, when we had s as a function of time, that displacement, we were really just, you know, we didn't say it at the time, but we were looking at what we call rectilinear motion, which is motion just along a straight line. Like imagine all you have is like a single axis and something's moving back and forth along that line. Now what we want to do is let ourselves consider an object that might be moving in 2 dimensions. So curvy paths, curvilinear motion. So the first thing we need to do, I mean, the way that we describe that motion, when you are given, I mean, we have curves in 2 dimensions. We've spent a lot of time looking at curves in 2 dimensions in the first chapter and all through pre-calculus, right? We graph functions, maybe quadratics or whatever, but we're used to seeing a representation of a curve in 2 dimensions as a single equation that relates x and y together. And that'll tell you where an object is, but it won't tell you when it gets there. So what we want to do, and one way to kind of get around that, is to, if we want to describe not just where an object is, but when it hits that, you know, time or that point in space, we can use parametric equations. That is, write a pair of equations, one for x and one for y, that tell us what the x coordinate is over time and what the y coordinate is over time. And if I want to trace out what the path is, what I can do is just put in a bunch, like if, you know, when we were first, you know, think back to pre-calc or algebra or whatever, the first time you start looking at graphing functions, one of the ways you do it in the beginning is, I'll just put in an x, figure out the y, get my pair. Put in the x, figure out the y, get my pair. So you could do something similar with some parametric equations. If I just let t range through, you know, the time, range through some values, and then find an x, y for each of those times. And then I'll kind of get this curve, and I could see not just where it is, but when it gets there over time. Those are what parametric equations are. We say that time, that third variable, is the parameter. And then to describe the velocity of an object, we're going to use vectors. So we're just going to go over some vector basics. If you haven't worked with vectors before, that's okay. I think what we're going to do here, we'll cover the basics. We'll cover everything we need to know. A vector is a 2-dimensional vector, is a quantity that has magnitude and direction. So we draw it like an arrow here. To denote the whole vector, we usually just put like a little half arrow over it to distinguish that from like just one of its components. In textbooks, they'll make it bold, but it's hard to draw it bold when writing, so we usually use that half arrow. So it's got magnitude. That magnitude is the absolute value of the vector. Absolute value always means distance to the origin. It's just that when we're doing absolute value of numbers, that distance, we have a kind of a simpler way to think of it. But it's always just the distance, so it's the length of this guy. And then the direction is this angle that we measure in standard position, so from the positive x-axis. Once you have a magnitude and direction, I mean, those are 2 quantities that define a vector. Another pair of quantities that could define a vector are, once you draw this vector out, just look at where it ends. Those coordinates of the point where it ends, we call those the components of the vector, the x and y components. And there's ways that we can relate them together, and they involve doing our favorite thing to do in the plane, which is to drop down a perpendicular. So if I knew what those components were, the coordinates of that point, well, the length along the bottom has to be the same as the x component, and this vertical length has to be the same as the y component. And we have a nice right triangle, so maybe we're not surprised to see this formula here that tells us the magnitude is the square root of the sum of the squares. That's just Pythagoras, right? Pythagoras tells us that bx squared plus by squared is the square root of the magnitude. If our vector is in the first quadrant, like if I just consider that, what that vector looks like here, using SOHCAHTOA, I know that tangent of theta is opposite over adjacent, so Vy over Vx. And that's true in any quadrant. Right? Tangent of theta is Vy over Vx. And so if tan theta is Vy over Vx, that means that if I want theta, I'm going to use the arctan function. Right? The inverse tangent function, just like we did when we were finding the inclination of a line, like way back in chapter 1. And so here, that's where this equation comes from. But notice I didn't just write theta, I wrote theta ref. That, for me, I'm indicating it's a reference angle, because the arctan function will not spit out an angle that's in quadrants 2 or 3 ever. And even if it spits out an angle that's in quadrant 4, it will express it as like a negative angle. It won't be from like 270 to 360. So what we do is, like, so if I do the arctan of, and notice I have Vy over Vx, but they're in absolute values, so I'm making everything positive, and I'm saying, please, please, please give me a first quadrant angle. That's my reference angle. And then if I want this angle, I just realized that that's this measure from the negative x-axis, that's the same as the reference angle. So looking at our quadrants, if our vector is in quadrant 1, then our angle theta is just the same as the reference angle, right? I mean, it's whatever you get when you use arctan. If we're in quadrant 2, that reference angle is how much I need to back up from the negative x-axis. So if I'm using degrees, then my angle is 180 minus the reference angle. If I'm in quadrant 3, that reference angle is this measure down from the negative x-axis. So what would I do to find theta in that case? 180 plus. And if I'm in quadrant 4, the reference angle is again measured from the x-axis. The reference angle is always a measure from the x-axis, right? And then what quadrant you're in just sort of tells you like in what direction and whether it's the positive or negative x-axis. How would we get our angle theta in the fourth quadrant? What's that? To what? To the reference angle? That'll give us a value. If I add 360, first of all, I'll be back in the first quadrant. That'll do the same thing. Yep. So notice that what I'm doing here is you could think of, if I'm moving in the clockwise direction, I'm backing up from something, right?
No, it's 480.
Say that again, Colin.
360 minus.
360 minus, right? That means go the full rotation and then back up by whatever that angle is. Angles. So we know that if we have found the components, if we know what Vx and Vy are, we can use Pythagoras to figure out the magnitude, and we can use the arctan function to figure out that the angle. And when we give a result as a vector, like if we're solving a problem and it wants to know what's this velocity, and it's a vector problem, we always want to give our result as a magnitude and direction, not just the components. Here's, to see why this comes up in this section in calculus. Imagine I have something moving along this path, right? So here's like the rectangular path that it's going through. It's parabolic in shape, but I mean, there's a path in the xy plane. And maybe I want to know, what's its velocity there? Like the velocity clearly is changing, right? Here the velocity vector is moving in this direction. Here the velocity vector is this way, and then it kind of turns upward. It's moving. There's 2 dimensions of motion, right? Like right at the bottom, the motion for an instant is only in the x direction, and the y component is 0, right? Like, because it's kind of leveled off a little bit. But if I kind of isolate a point and I say I want to know what the velocity is here, there's my velocity vector. I know it's moving partly this way and partly this way, right? As it's going through the curve. And so if I could find those two components, then we could do the things that we just talked about to find magnitude and direction. Now those two components, we're going to use calculus to find them. Vx, is how fast is it moving in the x direction? How is x changing over time? What's the rate of change of x over time? It's the derivative of x with respect to t. And Vy is how is it moving in the y direction over time? What is the rate of change of its y coordinate with respect to time? So Vy is dy dt. Notice that we are respecting time here in both cases. Let's do a problem. Some of the problems that you'll see in the exercises will be kind of like this one, in that they start out by giving us a set of parametric equations. Here I have x as a function of time, and here I have y as a function of time. If we wanted to plot this function, we could. And the way we would do it manually is just maybe time often starts at 0, so we could start time at 0 and then say, oh, I want to go up by quarter second increments or whatever, and I get a set of kind of discrete dots that we could sort of trace around. Our calculators will actually also do that for us. If you want to get your calculator to graph parametric equations, to graph a single curve, right? It's the pair of equations itself that correspond to a single curve in the xy plane. You have to put your calculator in parametric mode. So down here, it's in function mode. That's y is a function of x. But look, I could also put it in parametric mode. And when I do that, if I hit the y equals button, it changes. Now you see there's actually a pair of equations. Let me erase these. There's a pair of equations for each curve. Right, I've got an x1t and a y1t. They're both functions of time. So my x function is 3t squared. And now notice when I hit this variable button up here, it automatically changes it to a t because it knows I'm in parametric mode. 3t squared. And then my y function is 1 minus t squared. I don't know exactly what the right window is, but if I hit the window button, so I might kind of trial and error, see what it looks like when I graph it. But when I hit the window button, we have our regular x min, x min, y max. Then we also have our t min, t max. Where does time start? Where does it end? And the t step, how often do you want it to stop and plot a point? So I just put it at 1/100th, and maybe I'll let time. We were interested in what's going on when time is equal to 2 seconds, so maybe I'll just stop it at 3 seconds. And let's see. Oh, as it turns out, pretty darn linear. So I guess from this graph, it looks like we should expect the velocity to be in the fourth quadrant at least, right, when we find that angle. So let's do it. We need our components first. So our x function is 3t squared. So I'm going to find dx dt. What is dx dt?
6t.
And then to get vx, to get that component, I'm going to evaluate this at the time they gave us. So that's 6 times 2, or 12. There's our x component, positive 12. Our y function, 1 minus t squared. So we're going to find dy dt. What's that? What is it? Negative 2t. And so Vy, I'm going to evaluate this at that same time. which is -4. Now at this point, before I do any calculating, I like to make a quick note. What quadrant is that in if Vx is positive and Vy is negative? Fourth. Which is good. That's where it seemed like it should be when we looked at the graph of the curve. We have our components. Now we can use Pythagoras to get the magnitude, arctan to get the angle. That's 144 plus 16. 160. Now this is a application problem, so usually I go ahead and just get an approximation. And the square root of 160 is 12.65. It's the magnitude that has units with a vector. So reading through the problem, what should our units be for this vector? Their powers combined? Yeah, what per second? Yeah, centimeters per second, yep. And then it's dangerous at this point. This is the point of danger in these problems, because once we find the magnitude, often people think, all right, I've got the velocity, but I need to find the direction. So this is in the fourth quadrant, which means theta is going to be 360 minus arctan of. And when I throw these values in arctan, because I'm using this method where I'm just using the reference angle, I'm going to make sure I plug in positives in that in the arctan. So 360 minus arctan of 4/12. Well, let's see. Make sure we're in degree mode. You can use radians if you want. With vectors, I tend to see degrees used more often, and when you look up your results, like if you're checking your answers in the back, I'm pretty sure they're going to be using degrees. So in degree mode, we get 341.57 degrees. If you wanted it to be in radians, that's fine, but you'd also have to make this adjustment as well. So you wouldn't be subtracting from 360 anymore. You'd have to subtract from 2 pi. And then finally, the way we state our final result is that this is 12.65 centimeters per second at an angle of 341.57, or some people like to just write it as 12.65 centimeters per second at 341.57. They're both pretty common ways to denote the direction. How's that? If they give you a pair of parametric equations like they did here, the process, while it takes practice to get used to it, you'll find as you do them, it starts to feel kind of straightforward. Like, okay, dx dt, take the derivative, Pythagoras, arctan. Calculus is what we need to use in order to get these components. In this next example, they don't give us a set of parametric equations. In fact, they give us the rectangular equation. They say that a small sphere is constrained to move along a parabolic path, like maybe there's like a physical track, right? And that's the equation that describes it. And then they tell us that the horizontal velocity is constant at 6 centimeters per second. So because the horizontal velocity is constant at 6 centimeters per second, what information did they give us there? I mean, we've got that component, right? So I think we could at least recognize that most of our work is going to be in finding Vy. right? Because if I have Vy, then I'm all set. I can use Pythagoras and arctan. What piece of information did they give us here, other than just what the component is? Like what piece of calculus did they give us there? Yeah, with respect to time, right? So we know that dx dt is equal to 6 always, because it said it was constant at 6, and that's important. That means as a function, dx dt is equal to 6. Perfect. Okay. So our first goal here is to find dy dt. Notice I don't want to find dy dx. I want dy dt. The only y equation I have is this rectangular equation they gave us, though. Y equals 1/3 x squared. So we got to work with what we got. So we start with this equation, 1/3 x squared. And if I want dy dt, my only path forward here is to take the derivative with respect to t on both sides. So if I differentiate with respect to t on both sides, what do I get on the left side? dy dt. Yep. How about on the right side? How do we start?
You take the derivative,
Mm-hmm.
and then
So when you say take the derivative, like what?
1/3 times 2x
Mm-hmm.
times dy dt.
Close. You're right that like there's the chain rule that we have to worry about here. Nope. dx dt. We're respecting time, so it's definitely a dt on the bottom, but it's the variable of this. It's the variable of this variable with respect to whatever our important variable is. So that's why this was a dy dt, right? Because I was taking the derivative of y would be like 1, right? Times dy dt. We're respecting t, and this is a y. We're respecting t, and this is an x, so we got to multiply by dx dt. And we know what dx dt is. They told us it's equal to 6 always. So, see, 3 goes into 6 twice, times 2 is 4. So we get 4x. As a function of x, here's what dy dt equals, 4x. Now, they said find the velocity at the point 2, 1.33. Like, that's an xy pair, right? That's something along the path. And dy dt, as we have found, it depends only on the x coordinate. So I didn't need to know what time. I didn't need to know what value t. They gave me that point. So I'm just going to pick that x coordinate and throw it in this expression. And then we'll have vy. So vy is 8. What quadrant is this vector in?
First one.
Yeah, and why?
Yeah, because they're both positive.
Yeah, yep. So it's first quadrant, x and y both positive. That puts it in the first quadrant. That means I won't need to make any adjustments at all when I find theta this time. It's 10. What are the units on this magnitude? Yeah, it's going to inherit the same units that they used here to give us Vx. And theta, no adjustments needed, so it's just arctan Vy over Vx. 53.13 degrees. So our velocity vector is 10 centimeters per second at an angle 53.13 degrees.
And we didn't have to use the points there to find velocity because they were described by the function.
We needed to use this point here. We needed to use it to find Vy.
Okay.
Yep. Other questions? Okay. All right. So we can also find acceleration of an object. And we were, introduced to this concept in the last chapter. Acceleration is a rate of change of velocity. So if I know the position function, I just take the derivative again. It's the second derivative of position. So we just extend that idea to these parametric equations, to this scenario with vectors. So acceleration is a vector quantity. That means that we can find an x and a y component. They'll just be the second derivatives with respect to time of x and y, respectively. And once you, that's the only difference. Once you have those components, you're still back to just using Pythagoras and arctan to get magnitude and direction. So in this example, they want us to find the acceleration. And they gave us some parametric equations. And they didn't give us any units this time, so I guess our magnitude will not have any units, but that's one of the things you want to be on the lookout for with these problems. So if x is t cubed, we need to find the second derivative with respect to time. We start, of course, with the first derivative, which is 3t squared. Find the derivative again, get 6t. And so the x component, I'm just going to evaluate. I'm going to plug in t equals 2. So that x component is 12. Do the same thing with the y function. What's dy dt? And then we take the derivative again. What do we get? -2. Yeah. And then, that's pretty easy to evaluate, right? The y component is constant at -2. So that's our AY. And now this problem is, we're at the point where this part is identical in every problem. You've got your two components, then Pythagoras and arctan. What quadrant is this in? Y4. What? Yeah. Yep. So we're going to use Pythagoras to get magnitude. 144 plus 4 is 148. And that's about 12.17. This is where we'd put the units if there were any units given in this example. And then how do we get theta? Yeah, 2/12, right? Because we're just plugging in positives when we get that reference angle. You get 350.54. So there's our acceleration vector.
So what does that mean? Like from an object standpoint, is that speed enough for slowing down or?
Well, it's got, yeah, I mean, I guess it depends on, we might want to compare what the velocity is at that same point, right? But, and maybe compare it to the path that it's on. You know, like if we graphed this pair of equations, oops. I think I need to zoom out. Okay. Maybe I didn't need to zoom out quite so far, but. So, I mean, here's sort of the path that it's on. And you know how it, when it draws it, like the path when you see it being drawn out, and it does it kind of quick, so it's sort of hard to see, but like it started here and it went in this direction. And it's keeping, like that's over time, like that's actually like a time how this object is traveling. And so at t equals, so I think I went to t equals 3, so t equals 2 is maybe like right around here. And we could see like how it's going. The acceleration is still in the fourth quadrant, so I think it's actually speeding up, because it's in the same direction of travel. But acceleration is any change of velocity. So like, you know, you have to take into consideration the direction as well, you know, but like if it were 12 point blah, blah, blah in the, you know, and like maybe it was over in this quadrant, then I would probably view that as like, oh, it's kind of slowing down, like it's in like it's pulling in some other direction. One more. You want to do it? Let's do it.
I'd like to add a quick question.
Yeah.
Why do you use -2 when you're finding theta instead of just 2? Because AY is -2.
Yep, so when we're finding the reference angle,
Just don't worry about it. Just,
no, it's do worry about it. Make sure it is positive. The reference angle is a first quadrant angle. So we plug in positives, and then we account for whether those components are plus or minus by doing this process. We use that and we say what quadrant is it in, so I know what adjustments to make. Yep. Okay, let's do another one. Let's see, they give us some parametric equations. We have units in this one, nice, meters and seconds. We want both the velocity and acceleration vectors. So, maybe let's work with the x function first. So we find dx dt, which is just 45, right? So dx dt as a function is constant. That means that vx is 45. It's 45 when t is equal to 3 seconds. It's 45 when t is equal to whatever. It doesn't matter, right? And then, using this, and I know like it seems silly to make the distinction right now because these end up being precisely the same thing, but it's always using your dx dt expression as a function. That's what we're going to differentiate to get the second derivative. And the derivative constant is, of course, 0. And so the x component for acceleration is 0. Let's work with the y function. -4.9 t squared. So dy dt, what do we get for that? Negative 9.8 t, yeah. And so we could find Vy by plugging in 3 seconds. We get negative 29.4. Now we're going to have to take the derivative again, right, to get that acceleration. And again, we want to make sure, take the derivative of dy dt, this thing that is a function, not Vy, not this thing that is, if you use this expression after you've already evaluated it, like that's always going to be a constant when you find the component, right? So you want to make sure you're going back and using the function that you found. And we just get negative 9.8. So what is the y component for acceleration? Yeah. That kind of makes sense. I mean, here they just describe a scenario where they're just dropping a relief package out of a plane or something, right? It's dropping. So I'm pretty sure that acceleration in the vertical component should be negative 9.8 meters per second squared. Right? That's in keeping with what we already understand or have probably seen in a physics course. We have all the components we need. So let's find our vectors. Let's find, maybe we'll find velocity first. So 45 squared plus 29, negative 29.4 squared. .75. What are the units on that? Meters per second, because it's velocity. And what quadrant is that velocity vector in? Yeah, because x is positive and y is negative. So 360 minus arctan, and I'm going to plug in only positives into the arctan function. Vy over Vx, 29.4 positive over 45. You get 326.84 degrees. So our velocity vector is 53.75 meters per second at an angle of 326.84 degrees. Now the next one, acceleration. Our x component was 0. Our y component is negative 9.8. You can go ahead and use Pythagoras if you want, but what's the magnitude going to be? What is it?
9.8.
Yeah, it's 9.8. And we'll have a hard time using arctan to get the direction, but good news for us is I think there's a much easier way to find it. So here's our axes, right? This is, the x component is 0, and the y component is negative 9.8. So that's how it's headed, right? There's the acceleration, straight down. What's that angle? 270. So there's our acceleration vector, meters per second squared, at an angle of 270 degrees. Questions on that example? Yeah.
So what is a positive 9.8 is like that downward angle?
What?
It's absolute value of 9.8.
The vector? The magnitude?
Never mind, I think I'm good.
Okay. I mean, the magnitude is always a positive number.
Okay, there we go.
Yeah.
Perfect.
The fact that it's going downward
Yeah.
is indicated by the angle itself.